Hi there, my name's Jessica Hunt, and I'm here to talk to you about effects of universally designed serious games on students' fraction knowledge. So, to begin, I wanted to start with a little bit about the Model Math Education Program. We're funded by the United States National Science Foundation, and generally, our program developed and tested a game enhanced supplemental curriculum for fractions. The game, which is the heart of the program, is called Dream to Be. So I wanted to begin with you hearing a little bit about it from one of the students that engaged with it.
Christine, and I'm a sixth grade student in Brevard County, Florida. Today I will be introducing the game Dream to Be. This game introduces fractions.
Dream to Be is a puzzle-based learning environment where students master 3rd through 6th grade fraction concepts. The fraction concepts and skills in Dream to Be align with school curriculum standards. Players take on the role of Bunny, who encounters a series of challenges by engaging across 6 different STEM and ICT-based worlds. In each world, players access each challenge through a universally designed interface. Customizable features help create accessible gameplay for everyone. Play Dream to Be with a mouse and keyboard, or a controller. Players have a choice of tools that they can use to employ individual strategies and ways of reasoning. Sandbox Play supports players to create fractional quantities by partitioning, repeating, distributing, and coordinating units without high-stakes repercussion. Action adaptive prompts assist the player to notice their game-based actions and supplies reflective feedback. Prompts dynamically adjust to the player's actions and learning trajectory.
All right, so one of the goals of this project is to increase interest in quickly growing STEM careers. So here you can see how those careers are highlighted in each of the game worlds and the tasks that each world involves. These tasks, as you can see, promote students to build and quantify unit fractions, non-unit fractions, as well as build things like reversible reasoning and multiplicative reasoning. The tasks also support comparing and ordering fractions, adding and subtracting fractions, and multiplying fractions by whole numbers and other fractions. So the program as a whole is a curriculum. There are 36 lessons in this curriculum, which span the game worlds that you saw in the previous slide. And each of these 36 lessons generally has 3 parts: a launch, an opportunity for students to play the game, and an opportunity for students to engage in after game tasks and discussion. So let's look at each part really briefly. The launch introduces game narrative, or it connects to the STEM career that students are about to explore in a game world. They're very short. They're only about 5 minutes long, and they're really just meant to be a preview to get students going on the game or to connect to the STEM career that is the focus of the game. They're mainly video and question driven. We provide questions or scripting to teachers to use this part of the game. And here's an example of what one of those curriculum slides and materials might look like. This is in particular for the first lesson in World 2, which is a solar panel installer. And in this preview, the teacher is engaging students in a turn and talk about what they notice about the tools and bringing in their experiences with sharing things in their lives and connecting that to sharing and distributing the solar panels among the rovers. After that, students hop into gameplay. So this is where students engage in problem challenges, which are fraction tasks, and receive cognitive feedback. They play the game for 10 minutes, and gameplay is very much student activity driven with a focus on mastery. The game itself was designed using principles from Universal Design for Learning, and its features are really meant to provide access and engagement to students. 2 other prominent features the game relies on are, of course, the tasks in sandbox play mode, as well as the cognitive feedback. So together, these 3 design features provide opportunities for students to create and quantify fractions in tasks set along a learning trajectory, as well as support students to think through their gameplay. So this, there's not any sound on this, but it's really meant to just show you some of the features of universal design at play as students engage in one of the game tasks. So you might notice things about the multiple tools that students have available to them, um, multiple means of representing and accessing their knowledge, as well as expressing their knowledge as well. If this played through to the end of the task, the student would have multiple ways to express the quantity they created as they distributed the panels. This screenshot illustrates a few of the embedded universal design features. And again, part of the rationale for UDL is that if the game tasks aren't cognitively accessible to students, then they won't have opportunities for discussion and argumentation later in the lessons after game tasks. So things like universal design really help students connect to their prior knowledge and experiences as they play. This is an example of the cognitive feedback that students might receive as they play the game. Generally, the cognitive feedback is set according to self-regulated learning. So things like supporting students to set a goal. So different prompts might pop up either after no activity or if students engage in other activity. The prompts might help them also to notice and monitor their gameplay actions. It is very much based in the strategies that students use in the game. So in the example on the right-hand side of the screen, you'll see that the student has begun the strategy of distributing whole panels to each rover and has a leftover. So if they do that, they might experience this series of prompts. I noticed that you started by giving one solar panel to each rover. And can you use the fact that there are 4 rovers to help you share the final panel? The last part of the lesson is the after game task. So the after game task and discussion is really a pivotal part of the program. Each task either directly connects to students' gameplay or connections to a skill or procedure that the gameplay supports. And students really are using their gameplay to develop the concept. They use the after game task and discussion to connect concepts to larger ideas about fractions, as well as to connect concepts to procedural skills. So this is an example of one of the after game tasks that students might experience. It's called a game replay. And this particular replay is asking students to determine the equal number of panels each house receives when the number of panels is 1 greater than the number of rovers or houses. The problem results in a whole number of panels and a unit fraction of a panel for each house. And it is designed to connect the students' notions of whole number division. So teachers would start by asking students to represent on their paper or whiteboards how they might solve this problem or how they did solve it in the game. So that's why this task is called a game replay, because essentially they're representing their game-based strategy on paper or with models. And students may draw something like this or this. They might use the cubes to model the type of thinking that they originally employed in the game itself. And after a few minutes, students would then talk to a partner about their strategy. So you can see that we give a few questions for students to think with here. We also provide sentence starters in that paired share out, as well as during the whole group share out, which is the screen you see here. So in this part, the teacher leads a discussion highlighting the similarities and differences between 2 strategies and the quantification that results from each. The goal of World 2, ultimately in the program, is for students to realize that unit fractions 1 over b are the quantity formed by 1 part when a whole is partitioned into b equal parts, and that non-unit fractions like a over b are the quantity formed by 8 parts of size 1 over b. So for this share out, the teacher supports students to talk about how they knew how to partition those solar panels and how they quantified the share of solar panels for each house. And they use the teacher materials as a support to do that. You'll see here that the teacher materials are giving teachers talk moves used widely in the literature and mathematics education to support students to talk about and compare their strategies, think about what's similar and different about them, as well as connect them to larger ideas about the fraction concept, in this case, fractional equivalence. As the lesson wraps up, teachers finish by asking students, what did you learn today? And what helped you be successful in solving today's problems? So the work in this poster or this paper came from the gold phase of our research. And you kind of see our broad program research design over 3 phases, alpha, beta, and gold. And the work in this poster or paper is from the gold phase, where we used an experimental pre-test intervention post-test design. These were our research questions. Generally, we were looking to see were there differences in performance for students in the model meet group versus controls in terms of their fraction performance and scheme development. And were there differences in STEM interest for students who did or did not participate in the game-based intervention? So essentially, the Model Me program sat on top of programming that was already used in the schools. The only difference between the two conditions in the study was that Model Me was an added supplement. We worked with about 110 students across 2 schools and 6 teachers. The first school had 2 teachers, and the second school had 4 teachers. And both schools included students with different identities in terms of race, language, and disability. This intervention occurred in whole class settings, which means that it was being used with one teacher who taught about 15 to 25 students. The intervention in each school took place over 12 weeks, which is well over what is required best practice in terms of time period for technology-based interventions. And the screen here is showing you some of that demographic information. We had 3 measures in the study. The TIMA, or TAFA, pardon me, trajectory aligned fraction assessment is a modification of Batista's fraction assessment. It consists of 26 items, and it is a test of the curriculum. Items are based on the content of the 6 game worlds. It's a group administered test and has internal consistency reliability around 0.75, test retest about 0.86, and construct validity around 0.71. The fraction schemes test is a 12-item test of students' fraction operations and schemes. Specifically, it's testing the students' observable use of partitioning, iterating, and splitting, which is the combination of partitioning and iterating, as well as the measurement of schemes like the unit fraction concept. It was also group administered, and you see the reliability and validity information on the screen. For STEM interest, we used a survey called the Upper Elementary School and Middle School Student Attitudes Towards STEM, or the STEM. It was 20 items, which consisted for us of 2 constructs, which was math attitudes and math interest in STEM. It was group administered, and you see the reliability information for the assessment there. We also looked at engagement in terms of students' click trials in the game. We'll talk more about that in a moment. Our analysis of all of these data was in Miankova. Our dependent measures were the 2 fraction tests and the STEM interest survey. Our independent variables were the administration of these tests at pre-program, mid-program, and post-program, as well as condition. We also had follow-up analyses on this model using univariate ANOVAs. For engagement in terms of click trials, we looked at linear regressions. Specifically, we were looking at regressions between gameplay duration and gameplay tutorial duration with our measures. And here are some results. We wound up controlling for disability status due to significant difference on both pretest measures between students with and without disabilities, which was originally going to be a group that we were going to examine independently. Generally, what we see here was that the combined dependent variables were significant. And that there was a large, significant time by condition interaction effect. What you're seeing here for the curriculum-based measure. So essentially, over time, the control group stayed kind of flat in terms of performance, or even decreased in time 3, where the experimental group became significantly different in performance at time 2 and continued at time 3. For the test of students' fraction schemes, we see actually the experimental group performing slightly below the control and pretest, with their scores increasing over time as compared to, again, sort of flat performance in the control group. And those differences became significant as of time 3. For STEM interest, again, we had a significant time condition interaction. All of these interactions, by the way, were large effects. In this case, we saw both groups increasing in STEM interest to some extent, but the experimental group outperforming the control significantly by time 3. To examine the relationship between gameplay duration and gameplay tutorial duration, again, we conducted linear regressions, and what you see there is significant regressions predicting post-test CBM, fraction schemes, and STEM interest. So what this table is basically saying is that mean gameplay duration was a significant positive predictor of post-test conceptual understanding of fractions and STEM interest scores. Thanks for listening. I hope you found